Suppose a skydiver is starting from rest at a height h from the ground. Can we predict its velocity and position with respect to time? And how long does it take to reach 90% of the terminal velocity? In most cases, the amount of air friction will be proportional to the speed of the object and facing the opposite direction. We can model this with the equation F equals negative kV. Well, through force analysis, we can see that gravity is pushing him down while the air friction is pulling up. The net force on him is going to be mg minus kv, assuming that down is the positive direction. Acceleration is the rate of change of velocity, so we can write the equation of motion as m times dv over dt equals mg minus kv. This is a first-order, separable, ordinary differential equation, which we can solve by moving the v terms to the left, moving the t terms to the right. So we get dv over mg minus kv equals dt over m. So then we can integrate both sides, so we get negative 1 over k times natural log of mg minus kv equals t over m. Then we evaluate the left from the starting velocity to the final velocity. Remember that we set the starting velocity to be 0, and so we get negative 1 over k times natural log of mg minus kv over mg equals t over m. So then we can move the negative k to the other side, exponentiate both sides, and simplify, and we should get that v of t equals mg over k times 1 minus e to the negative kt over m. So to get the terminal velocity, you take the limit of v of t as t goes to infinity. The limit of e to the negative kt over m goes to 0, because e to the negative infinity goes to, well, 0. So the terminal velocity is mg over k. To get the time it takes to reach 90% of the terminal velocity, we set v of t to be 0.9 times the terminal velocity, which is mg over k. And so we set 1 minus e to the negative kt over m to be 0.9, and solve for t, so you get e to the negative kt over m equals 0.1. So we can solve for t, and we get that the time it takes to reach 9% of the terminal velocity, m over k times natural log of 10 seconds. Because we've set down to be the positive direction, to get the position, we put a negative in front to match the direction. Then we integrate v of t from 0 to t, then add the starting height h, so we get y of t equals h minus the integral of 0 to t of v of t dt. So integrating mg over k times 1 minus e to the negative k over mt, we get mg over k times t plus m over k times e to the negative k over mt. And so by evaluating from 0 to t, we get that our y position as a function of time is h minus mg over k times t plus m over k times e to the negative kt over m power plus m squared g over k squared. The following might not be entirely correct, for this is the first time I'm using this equation. If there are any mistakes, please correct me. So far, we've used force analysis to derive the motion formulas, but there's another way to derive them, and that's by analyzing the kinetic and potential energy of the system. The potential energy is mg times the height from the ground, which is called y of t, and the kinetic energy is the work done by the air friction. Wf equals the integral of f dy equals the integral of kv dy, which equals the change in kinetic energy, which is ek of t minus ek of 0. Since the skydiver is starting from rest, the initial kinetic energy is 0. Using the Euler-Lagrange equation, which says that the time derivative of partial L over partial Q dot equals partial L over partial Q, where L is the Lagrangian, which is the kinetic energy minus the potential energy. We're going to let Q be the current position from the ground. So Q dot equals dq over dt equals v will be the current velocity. The partial derivatives can be expressed like this. Side note, to take the partial derivative of a multi-variable function f of xy, you treat the other variable as a constant and differentiate with respect to your chosen variable. Here are some examples. So the Euler-Lagrange equation becomes the time derivative of mass times velocity equals mg minus kv. Using the product rule, the time derivative of mass times velocity is the mass times the rate of change of velocity plus velocity times the rate of change of mass. assuming that the mass stays constant, i.e. the rate of change of the mass is 0, we get that m dv over dt equals kv minus mg. Simplifying, we get that the net force is kv minus mg, exactly the same different equation that we've gotten earlier using force analysis. To see how close our v of t graph is to the vt graph without air friction, I've plotted both of them right here, where k is the air drag constant and m is the mass. As you can see, at k equals 0.05 or less, the two graphs almost overlap each other. When I make the mass lighter, the velocity with air friction starts to dip lower, which means it's reaching terminal velocity faster. This explains why heavier objects like a bowling ball falls faster than lighter objects like a feather. All in all, I consider air friction to be a measurably real phenomenon. In fact, there's a whole section of physics we haven't touched called fluid dynamics that talks about air friction a lot. And it also talks about the aspects that change the magnitude of it, like density, area of contact, etc. Maybe we'll talk more about fluid dynamics in future episodes. Well, that's all I got for today. See you next time.